So welcome to our seminar series in the Gemini Center on Quantum Computing. Our speaker today is Matteo from Algorithmiq. We're very happy, I'm very lucky to have him as a speaker. He obtained his PhD from the University of Milan in 2017. With topics on open quantum systems and quantum metrology. He then moved to the University of Turku in Finland, where he was worked together with Professor Sabrina Maniscalco on open quantum systems and complex quantum networks and quantum simulation. In 2021, he joined the PICO group at the Aalto University, also as a postdoc. Yes, where he was giving theoretical support to experiments on superconducting qubits. And then in 2020, he, together with Sabrina Maniscalco, Guillermo Garcia Perez, and Boris Sokolev, he co-founded Algorithmiq, which is a startup developing quantum-enhanced algorithms for life science. And he's a CTO as of now, as of this year of Algorithmiq. So without further ado, I think if you're ready, you can take it from here, Matteo.
Okay, thank you. So let me share the screen. Let me see. Do you see the presentation? Okay. Okay. So thank you very much for the introduction and also for the invitation to present our work. So the title of the paper is "Learning to Measure," and the kind of longer title is "Adaptive Informationally Complete Generalized Measurements for Quantum Algorithms." So it's we're basically dealing with the problem of estimating expectation values of observables on large, so on many-body quantum states. So this is somehow the overall topic. Let me acknowledge the authors of the paper. So there is a Finnish team, so it's Guillermo Garcia Perez, Boris Sokolov, and Sabrina Maniscalco, and myself. We are so we were working together at the University of Turku. Then we kind of moved in parallel to Helsinki, some to the University of Helsinki, and some other to Aalto University. And at the same time, we have been kind of starting this startup Algorithmiq, which, by the way, today we announced the first seed round of $4 million. So we are very, very excited. There's a lot of stuff happening. This paper was also in a collaboration with a group from IBM Research in Zurich, so the group of Ivano Tavernelli. And this is the reference. It was accepted. It was published like last, I think it was November of last year. So in this talk, I wanted to start with a kind of an invitation, so like a background problem for which somehow we started developing this method, which is the measurement problem in quantum chemistry and in variational quantum eigensolvers. And then I will explain, let's say, our methods, so starting from the generalized measurements and then our, let's say, adaptive measurement strategy, and present some results. I think so. I think in there are like I've seen there's people from so there's physicists, mathematicians, and also quantum chemists. I hope like everyone will somehow appreciate the discussion and the talk. And of course, you can ask questions at any point. So the starting problem, the general problem is finding, for example, the molecular ground state energy for a given molecule. So, for example, take water as an example. So molecule for which you have like somehow, you know, the composition. And you're interested in finding, for example, the ground state energy as a function of the relative distances of the nuclei. So finding the potential energy surface. And this in turn allows you to find, for example, the binding energy and determine reaction rates and other important information for chemistry. And if you want to do this, you have to essentially solve a time-independent Schrodinger equation. So you have, since your nuclei, you assume them to be in fixed positions, you have to solve the electronic Hamiltonian, so the Hamiltonian for the electron. And this is a many-body problem. The Hamiltonian itself somehow is easy to determine and to represent classically, but the issue is with the state of our n electron problem, because it's well, it's essentially in an infinite Hilbert space. But like what one typically does is go to a second quantization version of the problem in which you fix a basis of the, let's say, the positions in the position space of your electrons. So typically one has what you call molecular orbitals, so like a basis of functions in the three-dimensional space. And for each of these orbital, since the electrons have are particles with spin, you can have a spin-up electron and a spin-down electron. So each of these spin orbital, we call, can be occupied by one electron. So your state will be represented as a list of basically either zeros or one. So the list is a length m, depending on how many spin orbitals you are considering in your basis. In principle, potentially they are infinite, but you truncate at some point. So you have a zero if the spin orbital is empty, or one if you have an electron. So in the case of the water molecule, say that you are occupying all the first 5 spin orbitals, you will have a vector that is that looks like this. So 10 zeros, and then all the rest, 10 ones, and then all the rest are zeros, and so on. But in principle, you have all possible 2 to the m combinations of occupation configurations, and your state can be a superposition of these states. So the dimensionality is somehow classically intractable. It grows exponentially with say the size of the molecule. So people are now trying to solve these problems of finding, studying the chemistry of molecules on quantum computers. So there is an extra step that needs to be done. So the Hamiltonian for the electron is a fermionic Hamiltonian. So you have fermionic creation and annihilation operators for each of the spin orbitals. So you need to go into a qubit representation. So you need to map your problem onto a qubit Hamiltonian. And this is done. There are various techniques, but somehow this is not relevant. Once you have done this, the thing that the algorithm that people have been focusing on recently is this variational quantum eigensolver, which is a method that potentially allows the use of even the near-term devices that somehow we have access to, or maybe when they will be a bit more performing, which is basically using the variational principle of quantum mechanics. So you are fixing a certain family of states, which you call which is called variational form or ansatz. So states that are described by a set of parameters, and in the quantum computer will be implemented by a set of gates. So this is your state, which depends on a vector of parameters. So for fixed set of parameters, you can then measure the expectation value of your Hamiltonian. So this will give you the energy. And you know by the variational principle that this will be bigger or equal to the ground state. So if you then try to find a new set of parameters that mean that like has a smaller value of the energy, will get closer to the ground state. So essentially, you prepare a state, do some measurement, estimate the energy, then update the parameters and go on with your algorithm. And if you chose a variational form that is expressive enough, you can get as close as possible as the ground state. So in principle, you can even get the ground state or somehow get close enough to it. So this algorithm is promising, but of course has also many issues. One is the fact that, of course, the devices are noisy, so noise needs to be taken into account somehow. But then there are also problems with for example, the optimization. So how many parameters do you have, and like, are you getting stuck in local minimas? How do you choose the ansatz so that like you can reach the ground state? But somehow the problem that we were focusing on is actually in the measurement side. So in order to estimate this expectation value on a state that is large, you need to perform a lot of measurements. So you need to prepare the state many times and then project it somehow. And this has been identified as a roadblock somehow in the variational quantum eigensolvers. There's papers about it. And the reason is will be clearer now. So as I said, the electronic Hamiltonian has been transposed into a qubit Hamiltonian, and this qubit Hamiltonian can be expressed as a linear combination of operators pk, which are called the Pauli strings, because they are essentially a tensor product of Pauli matrices acting on each individual qubit. And this also includes the identities. So you will have essentially a long list of Pauli matrices, for example, along X and some identities and so on. So the expectation value of your state will then just be the linear combination of the expectation value of each of these Pauli strings. So somehow since the state lies in the quantum computer, this allows you to actually represent somehow to actually estimate the energy without having to write down this state on a quantum computer, which, as we said, is impossible. But then you need to, for each of these Pauli string, you need to perform measurements and calculate the expectation value, which means that you need to prepare your circuit, implementing your ansatz, and then projecting onto the various directions somehow for each given string. So if, for example, you have a ZYX string, you need to perform this measurement setting. If you have a Z identity X, you need to perform this other measurement, and so on. And then, of course, you need to repeat each of these settings many times in order to gather the statistics to evaluate the expectation value. And the overall error in the estimation will be given by the sum of all the variances for each of these Pauli terms. And then, of course, divided by the number of shots that you use for each. And then the problem is that in chemistry, Hamiltonian, for example, the number of Pauli string typically grows with n to the fourth, where n is the number of spin orbitals or equivalently of qubits that you are considering. So if for each of these you need to collect, say, thousands of shots for your estimation, the problem typically goes out of hand very quickly. And people, of course, have been trying to tackle this problem. Let's say a thing that one can immediately do is try to, for example, group Pauli strings in groups of strings that commute with each other, because that allows you to use one individual measurement setting to calculate multiple expectation values. And this is, for example, the case of these two strings. This string can actually be obtained by a measurement on this one by just marginalizing the projection of the second qubit and so on. But the problem with this method is that, first of all, you create some correlations between the different measurements of estimation of Pauli strings, and also calculating the group of commuting strings is not a trivial problem. Then there have been, of course, machine learning approaches to to this particular problem and in general to tomographic reconstruction of states. And more recently, there's been this paper of Preskill and others about classical shadow techniques, which is of course very interesting and very somehow popular at this point, and can also be used in the sense of estimating the energy value of a state. So what we proposed instead was to use generalized measurements. So in quantum information, we call them positive operator valued measurements. So they are more general than projective measurements because they are described by positive operators that somehow sum up to the identity. So the probability that your measurement will give a certain outcome is the trace of the state of your system times the operator I. And if this set of operators spans the space of linear operators on the Hilbert space of your system, then we say that the P of M is informationally complete, because if you collect enough samples, you're able to reconstruct the density matrix of your, so you're basically able to perform tomography. So in the case of a single qubit, for example, you need 4 linearly independent operators pi, which are also called effects of the P of M. How do you implement this on a, let's say, on a quantum computer, which usually involves the projective measurement onto the computational basis? There are many ways. A simple way is that of attaching to each qubit an ancillary qubit in some known state, apply it to qubit unitary, and then projecting onto the computational basis of qubits. And then you can assign to each of the 4 binary outcomes effects of a P of M. And if you have a multi-qubit system, then you just implement local P of M's for each of the qubits with this method. So what you will then obtain are lists of outcomes for the various qubits. So for example, you have numbers basically that go from 0 to 3 for each qubit. And we label this one of these outcome vector M. The probability of having this outcome M is the trace of the joint P of M operator times the density operator of your qubit, where the joint operator is just the tensor product of all the local qubit operators. And as I say, since each of these P of M is informationally complete, this allows you to estimate the energy, but also other things, as I will show you in a second. And you can also calculate, for example, the variance on the estimation of the energy. And you do this by doing the following. So first of all, you can, for each qubit, you can express the Pauli operators as a linear combination of the effects for your local P of M. So if your observable is, for example, the Hamiltonian is a linear combination of Pauli strings, then you can replace this linear combination in the formula, collect sums, and you have that your observable is the linear combination, is a sum of overall possible outcomes of your multi-qubit P of M multiplied by some weights, which are obtained by calculating this this sum and this product here. So now this is quite useless because, of course, this sum, so the possible outcomes of n qubit P of M's are 4 to the n. So there's exponentially many of these. But the thing is that when you calculate, when you want to obtain the expectation value of your observable, this is effectively just, so it's the probability distribution of the outcomes of the P of M multiplied by these coefficients omega m. So if you prepare your state on your quantum computer and perform many repetitions of this P of M, you're essentially doing a Monte Carlo sampling of this probability distribution. So you can calculate the expectation value of the operators by repeating the experiment many times. For each outcome that you obtain, you calculate this coefficient, which can be done somehow in a polynomial time on a classical computer. And then you calculate the average. And you can also get the estimation error, which is comes from the Monte Carlo estimation. So we tried this on some Hamiltonians for small molecules. So we simulated these experiments using the IBM simulator. And so this is the results. I'm showing first the Pauli, just a basic Pauli measurement, and also its optimized group Pauli measurement. And in this plot, you see the estimation error as a function of the number of shots that you're employing. Of course, so this is a log-log plot. So of course, you see that by increasing the number of shots, you have is 1 over square root of, yeah, actually this shouldn't be n, this should be s, or well, the number of shots. And if we use our method with 2 different informationally complete POVM, you see that we actually don't do much better than just Pauli measurements. But what becomes more interesting is when you look at how this scales with the number of qubits. So in this case, we took like a chain of hydrogen atoms. So by adding a new atom, you can increase somehow the qubit size of your problem. And if you use a Pauli, simple Pauli measurements, you have a scaling which is n to the 6 approximately. If you use the group Pauli, you lower the scaling a little bit. But if you use POVMs, you get to a kind of n to the 5th scaling. This was already somehow known with a similar method that people by Google devised. So they were using a sort of informationally complete POVM, although they fixed it somehow to a very specific one. And also they were doing a not very efficient classical post-processing. But somehow what we did further compared to this was to use the fact that we have informationally complete data from our POVMs, and the fact that you have somehow some freedom in implementing informationally complete POVM. So you can parameterize this unitary such that it satisfies certain conditions for which the POVM, the effective POVM will be informationally complete. So by optimizing the parameters here, we can adapt the POVM for the particular estimation problem that we want. And we can do this by estimating the gradient in this parameter space of the error in the estimation. And we do this without even having to, we don't need extra shots from the quantum computer. We can calculate that somehow with the shots that we already collected for estimating the energy. So we run a number of shots with a given POVM. We estimate the energy and its variance and the gradient with respect to the parameters of the POVM. And then we adapt the POVM and we collect more shots. And then we build up an estimation of the energy and its variance with all these collected samples. So eventually we can get an overall estimation of the energy. And this is what we get. So the starting point was the same as before. But by basically updating the POVM every certain number of shots, we can beat, you see, the group Pauli method. And we have checked this with many molecules, even increasing the number of qubits. And you see more or less the similar behavior. And if we now look at the scaling plot that I was showing before, so with the hydrogen chain, we see that the scaling goes down even more. And it is actually, it's around n to the 3rd, which is another scaling that was known also from another paper by Google. So Google is very interested in this measurement problem. They were obtaining this scaling with by basically adding a layer of rotation at the end of the state preparation circuit. But this layer of rotation, the depth of the circuit for this layer of the rotation is not scaling well with the number of qubits. So they were basically shifting the scaling in the number of shots into a like increasing depth of the circuit. So here we reach a similar accuracy with essentially an extra layer of unitaries. Of course, in all this, we are doubling the number of qubits. So of course, we are aware of that. But still, the complexity of the circuit is not increasing with the number of qubits. And the final thing that we are able to do with this data that we collect throughout our measurement is that we can, so it's informationally complete, so we can use it for estimating other things. In the paper, we, for example, took data up to 10 to the 5th, so 100,000 shots, and used it to calculate reduced, so to perform tomography of reduced k-qubit states. So for example, if k equal to 2, we are basically obtaining 2-qubit density matrices with all possible combinations of qubits. And this has applications. For example, you can use it for determining pairwise entanglement or other sorts of correlations. So we did show what is the infidelity in the reconstructed state. And as you can see there, the infidelity is quite low. Of course, it increases when you increase the size of the reduced density matrices. So k equal 3 means that we are reconstructing 3-qubit reduced density matrices and so on. This is because tomography is exponentially expensive. But so this is the data. This reconstruction comes from the data that we use to estimate the energy. And interestingly, we saw that basically by optimizing the POVMs for the energy, we were also improving the estimation in the tomography. And in another paper that is still on the archive, we use this informationally complete POVMs, for example, to determine experimentally, so on a real IBM device, the entanglement structure of a W state with 8 qubits. So seeing what kind of entanglement the device was able to obtain, and all this with the same technique of informationally complete POVM. So to summarize, the measurement problem is, so the measurement of expectation value of observables in many body systems is crucial also in many applications in quantum chemistry and, for example, also in condensed matter. But it is a problem because of the scaling of the number of repetitions that you need to prepare. So with this method, using informationally complete POVMs and this adaptive strategy, we're able to save on the number of measurements needed to reach a given accuracy. And at the same time, we can use the data to calculate other, for example, other expectation values or reduce the state tomography. And also let me underline the fact that somehow we use this for chemistry Hamiltonians, but somehow we don't make any assumptions on the type of state or Hamiltonian that we are considering. So the applications can go beyond chemistry and VQE. There are no assumptions or approximations that we make. So the only, let's say, approximation is the finite number of shots, so the estimation precision that you get. And also the scaling that we obtain is very promising. It's, of course, this is a simulation, numerical simulation. We don't have general proof, but somehow it looks very promising, and it's comparable to other techniques in the literature that have otherwise, but on the other hand, they have another cost, hidden cost somehow in the depth of the circuit. And this was the last slide, so thank you for your attention. Here there are some references. So thank you.
Yeah, thank you very much. That's very interesting talk. I think the floor is open for questions. Maybe I can, yeah, Simon, you go ahead. Simon, I think your hand was
I was
first.
applauding. I was not raising my hand, but I can still ask a question. It was a very interesting talk. I am very interested in reducing the error in measurements in variational quantum eigensolver. And I just, if I understood you correctly, the formalism that you presented allows you to measure a basis for the space of outcomes, so to speak. So if we do this on a molecule on the quantum chemical calculation, we will actually be able to assemble expectation values for other observables than the energy, right?
Exactly.
Yeah, this seems like a huge benefit over just computing the energy expectation value, because in quantum chemistry, one is definitely interested in other observables than the energy. I mean,
Exactly.
so that's I found that a really cool feature of what you presented. So okay, yeah, thank you very much.
Yeah. So and to comment on this, of course, yeah, there are, for example, we've looked into, for example, using the data for quantum space expansion techniques or similar things. And obviously, the thing that we have to investigate further is that, so if you, for example, adapt your POVM to improve the precision for a certain observable, you might have as a drawback that the precision for other observables instead gets larger. So there might be some trade-off, but for now, what we have been studying so far has shown somehow promising results also in this sense. But yeah, you're right. We can calculate many expectation values.
I mean, I guess most expectation values that we would be interested in are derived from the reduced one-body density matrix. Typically, but maybe that can simplify. I mean, maybe one, I don't know, but maybe, so let's say in a concrete application or implementation, so to speak, one would like to focus on one-body observables. Could that knowledge be used to tailor the implementation to make it more efficient? Or, I mean, so we are not interested in all observables, we are interested in these particular observables.
Yeah, I suppose it can be done. Of course, there is there is this step of the so when you say one body observable, we probably refer maybe to the fermionic description, right?
Yeah, sorry, yes.
So the issue, of course, is depending on what qubit mapping you're using. The one body fermionic problem might be cast into a many qubit problem, right? But there are, of course, you can choose mappings that try to keep it local in number of qubits as well. But yeah, I think you can maybe optimize at the same time multiple a class of observables. So, for example, many single body observables. I think that this can be done. This was the first work that we did in this sense, and we have many things that we wanted to look into in sense of seeing how good it is, let's say, when you consider other things as well. And thanks also for the input. And none of us is really an expert of quantum chemistry, so of course we might not even be aware of what is the most interesting things to do, let's say, with this.
I see.
Okay, thanks for the question and the answer. Jeroen, you have a question?
Yeah, just a short one. So in this adaptive protocol you showed, I mean, a great improvement in speed and so, but how does the complexity of the actual adaptation step, for instance, scale with number of qubits or problem size or so. Is that something to worry about?
I mean, it's a polynomial in the number of qubits, in the sense that, so what we need to do is calculate this gradient, which can be done like efficiently somehow using formulas similar to this one, let's say. So the cost, the classical cost, is in evaluating these terms here, but it's still a polynomial. Now I don't remember with what exponent, but it should still, like, I think it's still worth it to, for example, use that rather than using this, transferring this polynomial cost into the number of shots that you run on the quantum computer.
But that's not included in your n to the 3.3 or so.
No, that's just the scaling of the shots on the quantum computer. Also, all these techniques have an overhead on top of this scaling. For example, the grouping of Pauli matrices comes with the overhead of finding the grouping.
Of course.
So yeah, these are not taken into account in general, because somehow at this point, a shot on the quantum computer is somehow the costly factor in terms of time. But yeah, there is a overhead also on the classical post-processing. Yeah.
Okay, one question from me, because I think what you've done is using ideal simulators, right?
Yes.
No error models, and one of the downsides of your approach is that you double the number of qubits.
That is true.
So have you plans, or have you looked into a comparison of these methods, the standard methods that use half the qubits and yours, with an error model, and see how this affects
no, yeah, it's accuracy? A good point. We haven't done it. We have to do it. Of course, there is the issue that we're doubling the number of qubits, so and we also have some gates, because we have to do this unitary within each pair of qubits. But that somehow is this cost somehow should not depend on the number of qubits. So it's always the depth of this extra circuit is always the same regardless of the number of qubits. But of course, you don't know, for example, if the state of the ancillary qubit is exactly 0, or if it has decohered, or went to some thermal state, that we haven't checked in detail. We expect somehow that there will be a trade-off in terms of noise in that. But for example, this should be, as opposed, for example, to this method presented by Google with these Givens rotations at the end, that one will increase the depth of the circuit a lot. So there the noise will actually build up much more than in our method. But yeah, the noise, we need to run the simulation on the noise. Of course, this will reduce somehow the sizes that we can reach in the simulation. So hopefully we could even at some point try this on real hardware with IBM. Yeah.
Okay, thank you. Thanks very much. This was a great talk, and it was very interesting. And now I'm looking forward to read all the details in the paper.
Perfect. Thank you.
So now I think